A pendulum is another example of simple harmonic motion. Pendulum is just a mass, or a simple pendulum is just a mass hanging on the end of a string, and then gravity causes it to, go back and forth, and possibly hypnotize you. If we consider just the tangential force acting on, so we're going to say that this is the equilibrium position of the pendulum, this straight up and down, when it's hanging straight up and down. And the condition for simple harmonic motion was that the restoring force is proportional to the displacement from equilibrium. So let's think about this. If we consider the tangential force here, this force is caused by gravity, which we know is mg, and if we break that up into components, this is whatever angle the pendulum is sitting at. So this is mg sine theta is the tangential component of that force. So our tangential force is mg sine theta. All right. Now, if this angle is small, the pendulum is traveling close to a straight line. It's a curved path, as we know, but for small angles, we can assume it's basically a straight line. But it still is an arc length, and the length of that arc is equal to we know it's equal to the radius times theta. Generally speaking, we call the length of the pendulum, L theta. For small angles, sine theta is about equal to theta. So we can, if we say our angles are small, we can call this mg theta. And there we can see it's proportional to this angle. The restoring force is proportional to this angle. If our angle goes this way, the force is back the other direction. I should say minus, because it's always pointing back toward that middle position. If we have a positive theta here, then the force is going to be back this way. Right? Yeah. And using this, we can say that our theta is that arc length over L. So our force then becomes minus mg s over L. All right. And this, if we replace this arc length, this looks a lot like, it's kind of similar to minus kx. This is our kind of a distance from that equilibrium position, and this is a constant. So following that parallel, where omega for a spring is root k over m, we can say omega for a pendulum is root, this is like k, mg over L over m, and the m cancels out, and we get that omega for a pendulum is just root g over L. Right? So that's one piece of it, and then likewise we can figure out that our period is 2 pi over omega, which in this case would be 2 pi root L over g. So those are the properties of our pendulum motion and its simple harmonic. Remember, this is for small angles. In radian mode, sine of 0.4 is 0.38942, and this is about getting to the point where sine theta is not about equal to theta. So this is about the maximum angle. 0.4 is about, radians is about 20 degrees. So up to about 20 degrees, this pendulum motion can be considered to be simple harmonic, because that small angle approximation holds pretty well. Energy is a little bit, or potential energy anyway, is a little bit complicated for the pendulum here. It is only gravitational potential energy. It just makes, the math is just a little bit obnoxious. There's some trig involved. So this is L. So our delta H up to this point is what would determine the potential energy here, right? So our potential energy at a given point is going to be mg delta H. It's the height from this bottom. We call this our zero of potential energy. We can set that zero whatever we want to. Well, if this is angle is theta, then this is mg h1 minus h0, and mg, the height here, is this component, which would be L cosine theta. That's minus L. So our potential energy at a given point is mgl times cos theta minus 1. Right. So this is the potential energy at any given point on the pendulum's arc. And we can use that to solve energy problems. For example, we could say a simple pendulum with mass 0.12 kilograms and length 15 centimeters is displaced 8 degrees from equilibrium and released. I don't know, what's its period, what's its speed at equilibrium, what's its speed at 4 degrees from equilibrium. Period, this is a simple matter of applying our formula. Our period is 2 pi root L over G, so that's just 2 pi root 0.15 over 9.8, and we can punch that in, get 2 pi root 0.15 over 9.8, it comes out to 0.777 seconds about. What is its speed at equilibrium? Well, this is conservation of energy. At equilibrium, potential energy is 0, so we can say, and mechanical energy is conserved, we can say 0 equals delta PE plus delta KE. Our delta PE is 0 minus mgl cosine theta minus 1, which we can write as mgl times 1 minus cosine theta. And then we've got our 1/2 mv at equilibrium squared. So we can just punch our numbers in. Our mass is 0.12, 9.8, L 0.15 times 1 minus cosine 8 degrees plus 1/2. Mass is 0.12. And mass velocity at equilibrium squared. Well, mass cancels out. And we can punch that in and figure out what it is. 9.8 times 0.15 times 1 minus cosine 8 is 1.68 something. Sorry, I just realized I did my delta H backwards. This distance would be this distance minus this distance. So this should be L minus L cosine theta. So this would be mgl 1 minus cosine theta. So then down here, when it becomes negative, it is actually cosine theta minus 1. So it means that comes out negative, and then we move to the other side and it becomes positive. Okay, times 2 square root, and our velocity at equilibrium is 1.835 meters per second. Its speed at 4 degrees from equilibrium, well, again, we can say 0 equals delta PE, which is, we know our masses are going to cancel out, so we've got 9.8 times L times 1 minus cosine theta final, which is 4, minus 9.8.15 times 1 minus cosine theta naught, which is 8 degrees, plus 1/2 times mv squared. So by this subtraction, we can see that we've got 9.8 times 0.15, the 1's go away, and then we have a positive cosine 8 minus a cosine 4. And that's going to be, not equals plus 1/2 b squared equals 0. And we can punch that in and solve again. 9.8 times 0.15 times cosine 8 minus cosine 4. Shoot, I'm in radian mode. So I punch that in, and it's negative, good. Move to the other side, it becomes positive, times 2, square root of answer. And we get a velocity of 0.146 meters per second. I was in radian mode up here. So this number is wrong, this 1.835, but the setup is correct. 9.8 times 0.15 times minus cosine 8 times 2 square root. So this is 0.169 meters per second. Yeah, we can do conservation of energy problems with pendulums too, but then it gets tricky. Make sure you're keeping your calculator in the right mode, because when we're doing oscillation stuff with our simple harmonic motion equations, we need to be in radian mode, but then if I give you an angle of 8 degrees, you need to be in degree mode. So make sure you keep that straight. And now in reality, most pendulums aren't just a mass on a spring. Like if you've ever seen a big clock, it's like a long rod, and then it has a little ball of metal swinging back and forth down in the end. So when that happens, you have to take into account the moment of inertia of this pendulum. And I'm not going to work through the math because it's complicated, but the period comes out to 2 pi root L over G. So this is exactly what it was for simple pendulum. But then we also have to multiply by square root of the moment of inertia over ml squared. And this L now is no longer the length of the pendulum, it is the distance from the pivot to the center of mass. Because the center of mass, we treat the force of gravity as though it's acting on the center of mass. Fun little fact, if you treat the human leg as a physical pendulum, it has a period of about 1.6 seconds. And it turns out that the rate people naturally walk at tends to be related to this pendulum equation. So if a period of 1.6 seconds, your strides would be like half a period. And so people tend to take steps that are 0.8 seconds long when they're just walking along. And in correspondence with that, the average person tends to walk at about 1.3 meters per second.